Good day, and welcome to the Geo-Institute Technical Committee's web conference. Today's topic is shallow foundations. This is an audio web conference. You will hear the presentation through your computer speakers, and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking on the Ask Question button on the left side of your screen. Type your question into the box and hit the Send button to submit your question. I'd now like to turn the floor over to today's facilitator, Sadiq Khan. Sir, the floor is yours.
Thank you, Daniel. Hello, everyone. I'm Dr. Sadiq Khan, and I'm going to moderate the Shallow Foundation Web Conference arranged by the Shallow Foundation Technical Committee of Geo-Institute. I welcome you all to our web conference. We would like to thank to our gold sponsor, Keller. The connected companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide. By including all services in one contract, Keller reduces the client risk and ensures all aspects of a project are met on time and on budget. We have 4 speakers today and going to cover diverse area in shallow foundation. Each of our presenters will have around 22 minutes for presentation and around 5 minutes for answering the questions. Dear audience, please send us your question and our presenters will answer it at the end of the presentation. Our first presenter is Dr. Armin Stuedlein. Dr. Stuedlein is an associate professor of geotechnical engineering at Oregon State University. His research focuses on ground improvement, reinforced soil, foundations, and the characterization and incorporation of inherent soil variability and model transformation errors. Today, Dr. Stuedlein is going to present on updated bearing capacity models for spread foundation on aggregate pier reinforced clay. I'm putting him on.
Thank you, Sadiq. It looks like my slides have come up, so I'm going to go ahead and get started here. Just want to thank the technical committee for agreeing to host this presentation. Essentially, I'll provide a short introduction and background for the work, and then get into the main portion of the presentation to indicate the experimental basis for the models that we've proposed. Then we'll take a step back into the theoretical considerations for bearing capacity of aggregate pier improved ground and discuss the accuracy of previous bearing capacity models, and then begin to step through the various models we've developed using the existing database and some new loading test data that we've developed since then. So for those of you who might not be relatively familiar with aggregate piers or stone columns, I'll give a quick background. We're only going to talk about the action of these ground improvements in plastic soils. And in my experience, for plastic soils, whether we use a stone column or aggregate pier or call it a granular pile, they all seem to behave the same way. They follow the same mechanics. This ground improvement alternative does usually provide a cost-effective alternative instead of full excavation and replacement, and in some cases, deep foundations. Furthermore, it can provide a sustainable alternative for some of other construction approaches in that it reduces the excavation material volume, the duration of excavation, reduced material quantities, and you can also take advantage of using recycled aggregates in their construction. There are several types of aggregate piers, essentially kind of classified on how they're constructed. I think the first kind of aggregate pier, or really a stone column that was produced starting in the 30s in Germany, was by vibro replacement. And here the vibrator is used with a tremie pipe in a bottom feed method to construct the stone column or aggregate pier. But we can also construct a vibro pier, is the general term, where first a cavity is pre-drilled using soil augers, as shown in this photo. Then stone is placed from the top feed approach, and then the material is then compacted via vibration. Quite common and popular are aggregate piers that are densified via tamping. Here we've got essentially an excavator that has a hydraulic concrete breaker with a tamping foot, and the concrete breaker delivers short energy pulses to the tamping foot to compact the aggregate. Now, these are really not new types of construction. For example, the Taj Mahal was built in the 1700s, or even maybe the 1600s, using what we would call rammed aggregate piers, constructed using a free-falling dead weight, and that's still used in some parts of the world where labor is cheaper. So if we think about how we can apply ground improvement of aggregate pier type to spread footings, there's essentially four major configurations here, and I apologize, it looks like there's a plotting issue on my slide here, but essentially you've got a single pier given by caption A in the schematic, where the footing footprint and the stone column have the same diameter. Excuse me. In this situation, the area replacement ratio is 100%. Captions B and C show cases of intermediate groups of piers or single piers where the footing footprint may encapsulate all or part of the stone column as well as part of the surrounding soil. And then the more typical production condition of a group of piers where the footing footprint is much larger than the area of stone. And typically in production, you'll see area replacement ratios for static support ranging from maybe 15 to 40%, depending on the loading conditions. So let me go ahead and give you a quick background on the experimental basis for the bearing capacity models that we'll be talking about. And this largely stemmed from my doctoral work at the University of Washington. Around 2006 or so, we performed an extensive literature review and found 47 loading tests reported in the literature of shallow foundations on aggregate piers in plastic soils. And about a third of those were of good enough quality that we considered for the development of bearing capacity models. But clearly 15 loading tests is not sufficient to evaluate the accuracy of existing models or develop new ones. So we performed a rather extensive full-scale loading tests of 20 full-scale footings. These included 12 single-element tests or single-pier tests. 5 tests were on groups of piers with a 9-foot by 9-foot square footing, and then the remaining 3 tests were done on an unimproved subgrade using both the large and the small footings. At this test site, which was in Baytown, Texas, the subsurface conditions were your typical Beaumont clay, which is medium stiff in the near surface, grading to stiff as you go a bit deeper. Okay, so our test site is shown on the figure here on the left, kind of indicating the distribution of each individual loading test, as well as the explorations conducted to inform the model of the subsurface. Single element tests were conducted with a 2-beam system with 3 reaction points to transfer the uplift loads to helical anchors. And then the larger footing loading tests were conducted using a 6-beam reaction set with 8 anchors to generate the sufficient resistance to push the footings down. If we move on to the next slide, you'll see a comparison of some of the results from these loading tests. On the left-hand side, you see the large square footing on the unimproved soil that provides a baseline for the load deflection response. And we can see that as it approached the maximum load, we were deforming at about 125, 130 millimeters, or about 5 to 6 inches. In comparison, if we look at a shallow foundation resting on a vibro pier, in this case 10 feet long, it was pre-drilled and then vibro compacted, at the same maximum load, you're looking at about 60 millimeters or just over 2 inches of deformation. I've also got plotted the vectors of deformation adjacent to the footing, monitored with inclinometers and sondex. And you can see that the magnitude of deformations have been restrained with the vibro pier as compared to the baseline footing, and that essentially the load is transferred along the shaft of the aggregate pier to deeper depths, and so we don't have the near surface heave or outward movement of the soil as the soil approaches failure. So these kinds of loading tests were conducted to supplement the data that had existed and give a basis for evaluation of the bearing capacity model. So it does make sense for us to talk quickly about the failure mechanisms for the aggregate piers. So let's take a look at the failure mechanism of a single aggregate pier, and what we find is that the mechanism depends on the slenderness ratio, which we define as the length of the pier divided by its diameter. Essentially, from the literature and our own experience, if the slenderness ratio is less than 2 to about 3, then the toe fails in plunging, as there's insufficient length of the pier to resist the downward action along the shaft and produce a near-surface bulging failure that really takes advantage of the strength of the aggregate. Once the pier gets longer than a slenderness ratio of 2 to 3, then we initiate the bulging failure mechanism, which is really what you want to do in a design setting because you're taking advantage of the strength of the aggregate. The mechanism you see here, originally proposed by Bronze, is essentially a triaxial passive pressure failure mechanism, and we can predict using the friction angle of the aggregate what the active failure wedge will be in essentially an axisymmetric triaxial manner, and it's that passive pressure in the surrounding soil that provides confinement and strength to that aggregate that gets mobilized as failure is approached. This bulging failure mechanism has been confirmed in various experimental studies. An example of some experiments are shown in the figure on the right, and it wasn't a big stretch to consider the application of cylindrical cavity expansion theory to predict the capacity of a single pier. And so the approach here is to set the ultimate passive pressure in the soil surrounding the aggregate to be equal to the active pressure in the aggregate at failure. And so once we we equate these various earth pressures, we can arrange or rearrange the expressions shown here to obtain the capacity of the pier. Now, as you look at this equation, K sub P there, that's the cavity expansion factor, you see that it calls for use of the Young's modulus and the elastic constant Poisson's ratio. Now, I've always had a problem with that because at failure, soil is hardly nonlinear, is hardly linear, and so there's a bit of a philosophical problem here of using linear elasticity theory for a highly nonlinear problem. And sure enough, the cavity expansion factor is quite sensitive to the selected Young's modulus, which is a real problem of selecting which Young's modulus to use at a failure condition. Another approach that was suggested, in this case by Mitchell in 1981, is to boil down the problem to a simpler empirical approach, which we call the simplified method, in which a single aggregate pier bearing capacity factor is multiplied by the undrained shear strength to develop the capacity. Mitchell had originally recommended a bearing capacity factor of 25. The FHWA manual by Barksdale and Bacchus recommended a range of 18 to 22. Some loading tests were done in some soft clays in Thailand, and the resulting bearing capacity factors were 15 to 18. And so what we see is that the capacity then becomes quite sensitive to the value of the bearing capacity factor you've selected, and that can be quite problematic. Now, there are several other methods in the literature, just don't have time to review those here. Okay, so with our load test database, which included 30 different high-quality load tests, we're able to evaluate the capacity of single isolated piers, and we can do that by comparing the bias, defined as the observed capacity divided by the predicted capacity, and then the variation in the bias, which we use the coefficient of variation. That's just the standard deviation divided by the mean. The table shows that the bias on average could vary greatly from an underprediction of 250% with a variation of 30% to overprediction on the order of 50% with the bronze method with a bias of 0.64 and also produces significant variability in the accuracy. The simplified method by Mitchell could get to an average accurate value of bias of 1.01, meaning on average a perfect prediction, but you see that the COV is still quite large at about 25%. And that just happens to be the value for our database, so there's not a lot of predictive power moving forward. So we thought that we could improve upon these models by using a semi-empirical adjustment of the theory. And so we back-calculated key bearing capacity factors for the cavity expansion model and the simplified model. And we found that in back-calculating these factors, there's a significant influence of the undrained shear strength. And that's really not a surprise because the triaxial passive pressure in a plastic soil under undrained conditions is controlled by the undrained shear strength of that material. Furthermore, the relationship is negative, which means as the undrained shear strength increases, the unit increase into the cavity expansion factor decreases. The reason for this is that as the confinement on the aggregate increases, the tendency for dilation is suppressed. In other words, the friction angle of any granular material reduces with confining pressure, and we capture that mechanistic response in these semi-empirical adjustments. If we compare the bearing capacity extrapolated from each of the loading tests to that predicted using these two new models, we're able to see that we're quite accurate on average, and we've reduced the coefficient of variation to under 10% across the board. And so at the time, we were pretty happy with these semi-empirical bearing capacity models. So, these are for single isolated piers. What about groups of piers or intermediate pier conditions? What we did is we invoked the unit cell assumption in treating each aggregate pier below the footing to have some tributary area that controls its response. And it's quite common in terms of settlement analyses with aggregate piers to use this unit cell assumption where we essentially factor the stress distributed to the pier by its area replacement ratio, and then we add in the stress transfer to the soil by 1 minus the area replacement ratio. And so we adapted this approach for settlement calculations to capacity, where we would factor each calculated capacity, for example, the capacity of a single pier, factor it by its area replacement ratio, and then add in the factored capacity of the soil if there hadn't been an aggregate pier in place. And so this simplified approach was found to actually get to produce an improvement over the other methods that were available for groups of piers. Now, note, I'm not discussing the other bearing capacity models for groups of piers, but we did compute their accuracy statistics, and the bias was found to be highly variable and a COV of about 40%. That's really not good. If you look at our comparisons, if we discount the intermediate single piers, the bias is pretty close to 1 and a COV of about 13 to 15%. Including the intermediate single pier geometry, the bias is a little bit high with a general underprediction of about 10% and a COV about 30%. But in the meantime, since this was published in 2013, in the meantime, we've recently completed a new load test program, and so with our 8 new loading tests, we're able to further update our bearing capacity models. And in the previous models, we really didn't account for slenderness ratio directly, and we only indirectly accounted for confinement of a single pier below a footing in a group pier configuration. And this led to the poor accuracy for some of the pier cases like the intermediate single piers, the intermediate groups of piers, and the group of pier. So we thought we would be able to take a new hack at the bearing capacity models to be informed by the new data and see if we can account for some of these known variables a little bit better. So if we look at this little schematic in the upper right-hand side, we now want to account for the confinement produced by the soil surrounding the pier. And we're not necessarily talking about the stress per se directly, but rather the volume of soil that is confined below the footing, and account for that, the extent of confined soil to better improve the capacity. So we back calculated the capacity of a given pier below the footing as it lies within the group, so quite a bit different from the single pier capacity discussed earlier, and we can back calculate it using the same general approach that was proposed in 2013. And what we see is that there's a significant relationship between the capacity of a single pier in any group as a function of the area replacement ratio. And you can see that capacity of that pier really depends on the volume of confined soil surrounding it, and that explains the negative relationship between the capacity of that single pier and the area replacement ratio. There is some scatter here, and that has to do with the effect of slenderness ratio, and so we'll get into that shortly. So we propose new models which are not being shown nicely on my slides. I hope they're being shown nicely on your slides. That includes the confinement effect. Each of these new models have two components. One is the capacity of a single pier, that's again factored by the area replacement ratio, and then the capacity of the unimproved soil, which is also factored by 1 minus the area replacement ratio. The new item here is that, number one, we've recalibrated the N sub P and the K sub P factors, which are the bearing capacity factor and cylindrical cavity expansion factor, but we've also added then this confinement factor, which is a function of the area replacement ratio. The newer capacity factors now include both undrained shear strength and slenderness in their general terms. So if we go to the next slide, we can show the actual formulations for these new factors. If these slides are not available after the talk, you can always email me for a copy of these slides. But here we can see the new formulations for N sub P, accounting for slenderness, and then here's the back-calculated empirical confinement effect factor. And regardless what model you use, either the simplified model or the cavity expansion model, the confinement factor is the same because the effect of confinement is the same on the aggregate pier. So we want it to be philosophically consistent. On the graphs on the right show a single solid curved line from the previous models that illustrated how these factors varied with undrained shear strength, and there's only one line because it doesn't account for slenderness ratio. The remaining lines show now the effect of how the slenderness governs these bearing capacity factors. And if you've got a short stubby pier with a slenderness ratio of 2, when you go from a slenderness ratio of 2 to 5, you can see there's a big change. But as you get longer and longer, that change diminishes because once the shaft has sufficient strength to force the bulging failure mechanism, there's only a small incremental improvement in the capacity. And so we're able to capture that. Slowly wrapping up here, the accuracy of these updated models have been improved relative to the previous model set, with a bias on average of 1.0 and with a coefficient of variation all less than 20% depending on the design configuration that you have. And so now we feel like we're capturing the mechanics governing the capacity of aggregate piers quite a bit better, and we're able to make an improved prediction of the performance under shallow foundations. So to wrap up here, I think that we've been able to continue improvement of the modeling of the capacity of these systems. And while we use theory as our starting point, and we always want to keep an eye on the mechanics, I think that using full-scale loading tests to to account for the observed performance and the collective experience of the industry is a good way to go. And certainly these loading tests continue to play an important role in the improvement of our models. But that doesn't mean we don't need to perform site-specific loading tests to confirm performance. Those are always recommended from a quality control standpoint, and also will help provide data for further improvements. In closing, and then I can be happy to take any questions that might exist, I want to thank my collaborators, John Martin, my master's student who conducted the new loading tests, and my colleague Taeho Bong, postdoc who recently concluded his work here at OSU, for their support and help in developing this approach. So with that, I'd like to turn it back to Sadiq and take any questions that might be having. Hello, Sadiq. Okay, well, it sounds like there's no questions, and I'll turn that over to Diane.
Okay, next up we have Zhan Zhang, who will be presenting modeling residential buildings on expansive soils in response to climatic conditions. Sean, take it away when you're ready.
Okay. I'm ready, but yeah, okay. Good afternoon, everyone. My name is Xiong Zhang. I'm from Missouri University of Science and Technology. Today's presentation is part of my doctoral work when I was a PhD student with Professor John A. Burrell when I was at Texas A&M University. The topic of my presentation is modeling residential buildings on expansive soils in response to climatic conditions. Oh, sorry. What's the problem? I cannot see the slides. Oops. Okay, this is the outline of my presentation. First, I will give a simple introduction regarding the background of the research, and then I will talk about the models needed for the simulation and the laboratory tests to characterize the material properties, and then a verification of the proposed models. After that, I will give some examples of numerical simulations, and some conclusions will be derived from that. So this slide shows the distribution of expansive soil in the United States. As you can see, it is extensively distributed in the United States and covers roughly about 1/4 of the total area of the United States. And then every year, the damage caused by expansive soil is huge. As you can see in this slide, which shows some statistical data, in 1987, the total loss is $9 billion per year, which exceeded the total loss caused by earthquake, floods, tornado, and hurricane for that year. It was the largest geohazard in the United States until Hurricane Katrina. So the problem with the expansive soil is when it gets water, it works well, and when it loses water, it will shrink. So when you build a residential building on expansive soil, normally the soil underneath the center will have a constant moisture, relatively constant moisture content, but the soil at the edge of the house, the moisture content will change significantly, which will cause volume change of the soil and the differential settlements below the foundations. If the differential settlements are not enough, it will cause damage to the house. So here are some examples for the damage caused by expansive soils. Yeah, this is related to a tree, which can absorb a lot of water and then cause damage to expansive soil. So normally we have some kind of foundation design to try to overcome these problems. The most frequently used are the stiffened slab on grade or elevated structure slab on piers. For this simulation, we are mainly focused on the stiffened slab on grade. So a little bit background about existing research, because the problem is very complicated. So in the past, normally we divide the problem into several small problems. We often use a two-step approach. In the first step, we will do a single one-dimensional or two-dimensional numerical simulation to simulate the moisture content variation below the in the soil below the slab, and then from there we can calculate the differential settlements caused by the coverage. And then in the second step, we will use apply a plate and force it to fully contact with the deformed soil to calculate the bending moments and the shear stress in the slab for design purpose. So this slide shows some of the existing research and their limitations. In a summary, the limitations of existing research are as follows. In the first step, many simulations are just one or two-dimensional. It cannot consider the coupling between water flow and deformation, and the climatic effects are not accurately considered. In the meantime, very often, the constant material properties are used for soils. In the second step, very often soil is considered as solid without water inside, and we use either wetland foundation or elastic half-space foundation model to simulate the soil structure interaction. I will talk about the limitation for these kinds of models later. And then it can neither simulate the separation or friction behavior between the soil and the slab. In addition, according to our knowledge, there is no existing research consider the influence of superstructure. In other words, the major limitation for the existing research is the soil, the slab, the superstructure, the soil structure interaction, and the climatic foundation has never been simulated in a single whole system for the foundation on expansive soil. So for this research, you are trying to overcome the limitations in the existing research and try to simulate all these components in one single simulation. So let us take a look at what we need to be included in the simulations. First, we need a model which can simulate the behavior of expansive soil. Expansive soil can deform under the influence of both mechanical stress and moisture content variation. As a result, we need a coupled hydromechanical stress analysis to simulate the behavior of the soil. In addition, we need a model which can quantify the influence of climatic conditions. So we need to know how much water is going into the soil due to the rainfall infiltration, and how much water is lost due to the evaporation or evapotranspiration. So we need a model which can be used to define the boundary condition by using a daily climatic condition. The third one is we need a model which can simulate the soil structure interaction, and we also, because the slabs are often very thin compared with its other two dimensions, so we need to use special kinds of methods to simulate that behavior. Also, the walls of the rest of the foundation building also is very thin, so we need to use a plate or shear theory to simulate that behavior. Finally, we need a model to tell at what time there's a crack, and if there's a crack in the slab or in the superstructure, how the structure performs. So let us discuss it one by one. So as we discussed previously, the volume of the unsaturated expansive soils are influenced by the mechanical stress and also the moisture content variation. But their influence on the volume change are different. For the mechanical stress, if we apply load in one direction, the soil will deform in three directions with different magnitudes. But if we add water or take water away from the soil uniformly, the soil will deform in what directions with the same magnitude. So this kind of behavior is very similar to the coupled thermal stress problem, in which the heat energy is corresponding to water content and the temperature is similar to the influence of matrix suction. And then we derived the differential equation for the volume change of unsaturated expansive soil, which is shown in this slide. The first three equations show the force equilibrium in the X, Y, and Z directions with consideration of mechanical stress and the suction change. And the force equation are the what mass conversation for what flow in unsaturated soils. I would like to emphasize that these equations can be used for both saturated and unsaturated soils. For saturated soils, there is a relationship between the material properties, and the above four equations becomes a bioconsolidation equation for saturated soils. And we also developed some simple methods to measure the soil properties needed for the numerical simulation, which include the one-dimensional consolidation test, phase well shrink test, and suction test, and the specific gravity test. We have published a journal paper in ASCE Journal of Geotechnical and Geoenvironmental Engineering. So due to the limited time, I will not discuss this in detail. And from this test, we can generate two constitutive surfaces for unsaturated soils. One is for the volume change, represented by void ratio as a function of matrix suction and mechanical stress. The other is the relationship between water content and mechanical stress and matrix suction. By taking the partial derivative of these two constitutive surfaces, actually we can get the material properties needed for the simulations, which including the Young's modulus, coefficient of expansion due to matrix suction change, and the specific watt generation coefficient. This parameter will tell you if you apply load to the soil, how much water can be squeezed out of the soil. And the last one is the specific water capacity, which is the slope of the soil water characteristic curve. But as you can see, the soil properties are highly nonlinear, and all of them are functions of both mechanical stress and matrix suction, which make the problem highly nonlinear. The next problem is how to deal with the boundary condition. The boundary condition including two parts. One is the rainfall infiltration, which is relatively easy to handle. The difficult part is the evaporation process. Many factors influence the evaporation process, which including the solar radiation, air temperature. These two will provide the energy which can change the liquid water into water vapor. And then the relative humidity and the wind speed will have influence on the speed of how water vapor is removed from the ground soil surface. These are the water vaporization and the vapor removal are two important processes in the evaporation process. Other factors also influence the results of the evaporation or evapotranspiration process, which are vegetation types, soil permeability, and soil water content. For example, tree has different ability in absorbing water from the soil than grass. And if initially the soil is dry, even if it is a very hot day, the actual evapotranspiration will be zero. And in the past, the research for evapotranspiration process was mainly done in agriculture engineering. So there are many methods has been developed to estimate the evapotranspiration process by using daily climatic condition. The method we used in our research was called the FAO payment monthly method. It is an international standard. It is globally valid, and it can use daily or hourly climatic data to calculate the evapotranspiration process. It considered both the water vaporization and the water removal process, while other methods such as temperature methods and the radiation methods only consider part of the process. So this is a more accurate method. So this slide shows the equation used for the payment method. As you can see, there's Rn is solar radiation, and T is the temperature, and the U2 is the wind speed, and ES and EA are related to relative humidity. In addition, there are some kinds of correction coefficients which can consider the influence of different kinds of vegetation and the different water content situations. And for different kinds of boundary conditions, such as bare soils, grassroot zone, and tree root zones, we also have different methods to consider their influence. For example, for tree, we consider that most of the rainfall are intercepted by the tree so that there is no infiltration can happen in a tree root zone. But this is just a first approximation. And then we also need a model which can simulate the soil structure interaction. So this slide shows two situations. One is the azimuthal case, which is corresponding to the situation during a rainy season when there is a lot of rainfall infiltration and there is a swelling of the soil at the edge of a slab. And the second case, which is a centennial case, which is corresponding to the situation in a very hot season, and there is a lot of water loss from the soil at the edge of the slab. So as you can see, the shear load the load from the superstructure could be not uniform. Sometimes the slab and the soil can be separated, and there could be some kind of frictional force between the soil and the slab. All of this should be considered in a simulation. In the past, we often use the Winkler foundation to simulate the soil structure interaction. The limitation for this method is it cannot simulate the friction because it assumes the soils are not of independent linear elastic springs. So another limitation for this model is it will underestimate the bending moment. For example, if you have a uniform load from the superstructure, there is no bending moment in the slab, but in reality, due to the shear stress between the soil columns, there could be some kind of bending moment. Some researchers also use the elastic half-space foundation model to simulate the soil structure interaction, but this model is very difficult to implement. It's very difficult to simulate the separation or friction between the soil and the slab, and it requires the soil beneath the slab is uniform everywhere to a depth of infinity. This is very difficult to achieve because even for the same soil, if the moisture content is different, the modulus of the soil could be significantly different. So it will be very difficult to find the equivalent Young's modulus. So what we used was the jointed element or compacted element we borrowed from rock mechanics. The bottom of the slab is the top of the compacted element, and the top of the ground soil is the bottom of the compacted element. So during the simulation, actually, the program will calculate the thickness for the compacted element, which is the distance between the slab and the soil. If the distance is 0, and then any load can be transferred from the top to the bottom. If the distance is greater than 0, then there's an opening between the soil and the slab. No load can be transferred from the top to the bottom. And then we also can consider the friction behavior by using the equation below. The next part is we need a model which can simulate the behavior of the slab and the walls. The characteristics of the concrete slab and the wall for the residential building is its thickness is very, very small compared with the width and the length. As a result, if we use conventional three-dimensional finite elements to simulate it, it will cause some numerical singularities. So some researchers use the Kirchhoff plate theory to simulate it. It can only simulate bending, and some researchers also use the Mandolin plate theory to simulate its behavior, which can consider pure bending and shear deformation. But for our situation, if we would like to simulate the 3D dimensional behavior of a residential building, there could be some kinds of pure bending, shear deformation, and plate stretching. So this is the reason why we use the general shear elements to simulate the behavior of the slab and the walls. It has 5 degrees of freedom. It is more accurate. And then its middle surface can be arbitrary, and it can be used for both thick and thin shears. So we try to put everything together, all the models together, but when we try to put everything together, actually we encountered difficulty because this is not simply just add a thing together. If you look, the reason for this is if you look at the soil, we're interested in both the moisture content variation and the mechanical stress and how it will influence the soil behavior. And then for the superstructure, we are only interested in the mechanical stress. So there is inconsistency in terms of the analysis types. So what we did was we developed a pseudo moisture variation method to overcome this problem, which is for the superstructure and the slab, even though there is no moisture content variation or we're not interested in it, we're still using a coupled hydromechanical stress analysis to simulate its behavior, so that the whole system is a coupled hydromechanical stress analysis, but we assigned some special material properties to the superstructure so that the added water content variation will not influence the simulation results. So we have a test site which is built in Texas, Arlington, Texas. We built 4 footings, and every 1 month or 2 we went in there to measure the moments of the 4 footing under the influence of the climatic condition. We also took some samples by getting the and take it back to test the soil properties. So this is the climatic condition we collected from local weather station, which included the mean temperature, relative humidity, wind speed, and the rainfall. The solar radiation we also have it, but there's no space in this slide, so we did not include it. So this is the obtained moments for the 4 footings over a period of 2 years. As you can see, in the first year, the moments of the 4 footings are relatively small, and then we have a very big drop in the summer of 2000, and then followed by a big jump back in the fall of 2000, and it come back to its relatively its original position in spring or summer of 2001. So we used our model to simulate the behavior of the 4 footings. And this slide shows, the upper one shows the daily rainfall data and the daily evapotranspiration data, which is represented by the yellow fonts. And the lower part, the moments of 4 footing were copied from the previous slide, and the blue line represents the moments of the 4 footing we simulated. As you can see, our simulation does not match the measurements perfectly, but it reasonably reflects the tendency of the 4 footings. As you can see, the reason for the little moments in the first year was because the rainfall and the evapotranspiration were relatively evenly distributed. As a result, there is little moments for the soil. I would like to mention that for our simulation, every day we have a simulation, but for the measurements, it's monthly measurements. So, this is the reason you can see some of the differences between the simulation and the measurements. And then we have a very dry summer without even 1 drop of rain. This was the reason why there is a big drop. And then it is followed by a very rainy fall season. That was the reason why the 4 footings went back. And then, So this part, the going up part, we did not simulate it very well. I think it might be related to the permeability function we selected, so we need to do more research in this aspect. The problem with the simulation is the 4 footing just represents 4 points in the field. In reality, we are more interested in knowing how the climatic condition influence the structure behavior. So after the model was verified, we try to use it to simulate a virtual house. So we built a 4-bedroom with a car garage house by using supercomputer, and we also put a tree there at the corner of the house. This slide shows the distribution and the dimension of the simulation. So this is the layout of the simulation. So we have doors, windows, car garage, and a tree. And the stiffened slab, we use the equivalent uniform slab to represent it. So this slide shows the matrix suction distribution at different time of the simulation from the very beginning, which is August 31st, 1999, to June 16 of 2000, and there's relatively small moments. And then at the end of the dry summer, we have very dry soil, which is represented by the situation on August 1st, 2000. If you look at the surface, the dark surface means the soil is very dry. In the meantime, because of the coverage of the soil, the soil beneath the slab is relatively wet, and then at the end, the moisture content at the surface is recovered. So this one shows the opening between the soil and the slab. As you can see, at the corner, actually there's an opening between the soil and the slab. This is where the tree is located, because the tree has a high ability to absorb water, which causes a large separation between the soil and the slab, but it can recover in response to the climatic condition. And then they show the contact pressure between the soil and the slab at different conditions. When the soil is dry, very dry outside, as you can see, there's a contact pressure between the soil and the slab is very big. Okay, I will try to rush to the end. So this is the shear stress between the soil and the slab. This is the bending moment along X direction at the different locations of the slab. For design purposes, we can find the maximum bending moment and the minimum bending moment in the slab for a period of 2 years. And then we can also find the stress in the superstructures. For example, at the corner of the door and the corner of the windows. So these are the conclusions. We developed a complete system for the simulation of the restoration building on expansive soils, which exists, overcomes many limitations of existing research. So, we use the different kinds of methods to deal with different kinds of boundary conditions, and use the different methods to predict the different components with the best accuracy. And we found that the tree has great influence on the behavior of the building, and we think we need to provide some modification for the existing design criteria. So thank you very much.
Thank you, Sean, for your presentation. And I think we don't have any questions or answers for this, so I'm moving to our third presenter. Our third presenter is Mr. Lyle Simonton. Lyle is the Director of Business Development in Subsurface Constructors, ASCE, and he is going to present on implementation of pipe ground improvement and earth retention for the Straits of Central Development. Lyle, you are on.
Thank you, Sadiq, and thanks to the technical committee for allowing this presentation today, and thanks for everybody attending the presentation, the title of which is Implementation of Ground Improvement and Earth Retention for the Streets of St. Charles. Now, the title is slightly misleading in that although earth retention was a big component of this project, time won't allow us to really talk about it too much, but it does play a role even in the ground improvement part of the construction, the design and construction on this project. So you will see some slides of the earth retention, and I'll touch on it, but probably not give it its due time, considering this is a shallow foundations webinar. Just to introduce the project, this is more of a case study than the prior presentations you've seen today. I think Jean-Louis has a case study on the Washington Monument, so I guess this is the case study half of the webinar. And you'll see some similarities in the discussion today on what Dr. Stuedlein presented with aggregate pier design. So this particular project is a mixed-use facility, one of the first of its kind in the St. Louis area. I know we've probably all been involved in several mixed-use projects. It's a lot of development going on this type where you have office and retail, commercial, that sort of thing. So why is this project relevant for a shallow foundations webinar? We're going to talk mostly about ground improvement. However, as Dr. Stuedlein pointed out, oftentimes the reason for using aggregate piers or stone columns, and I'll use those phrases interchangeably, but the reason for using that type of ground improvement most often is so the structure can be built on shallow foundations. And when that's the case, it's cost effective when compared to remove and replace or deep foundations. On this type of a project where we're using aggregate piers to support structure, if it's just a straightforward aggregate pier project, I probably wouldn't present it for a webinar. However, this one is unique in that we designed and installed several really stone column ground improvement for all the structures, but used several different techniques due to the variability of soils on the site. Not just the variability of soils, but also significant grade change across the site and how all the structures were sequenced in their construction, and the earth retention system that I mentioned that we also designed in construction played a role in that sequence of construction. So as I mentioned, significant grade change, not necessarily, although I say challenging, that's probably not the best word. The soils themselves were not that challenging. The cohesive soils were pretty good strength, and the sands and silty sands weren't that bad. But because of the variability across the site and how many structures went in and the earth retention system, the challenge was changing our installation technique for stone columns and in some cases grouted columns to deal with those variable soils. So I'll show you several structures here, all of which are supported on stone column ground improvement. As I mentioned with the sequence of construction, we have 4 structures here and 4 building structures, and then a permanent shoring system were part of the work of subsurface constructors. And I just point out the large MSE wall. You'll see it in a lot of the photos. We didn't have anything to do with that other than the fact, I guess, it tied into our permanent shoring system. But I'm presuming most of our audience are geotechnical engineers, and this is one of the biggest, if not the biggest, MSE block wall in the St. Louis area. It's roughly 30 to 32 feet high, and it's really a neat looking wall, and you'll see it in a lot of photos. So I thought it was worth pointing out here, although I won't have any time to really discuss how the shoring system tied into the MSE wall. The site's located in St. Charles, Missouri, which is about 20 to 25 minutes west and north of downtown St. Louis, Missouri, as you see in the upper left-hand corner in the map. I'm not sure how well that comes across on your screens. Hopefully you can see that. The Streets of St. Charles development is in the southwest quadrant of the intersection of Interstate 70 and the Missouri River. So as you see in the Google Earth photo pointing out the Streets of St. Charles development, and that's a photo of it after completion, and with its proximity to the Missouri River. So as you can imagine, we have some alluvial soils here due to the proximity of the river, but in this particular photo from right to left, you have a pretty substantial grade change, which I'll point out on the boring location plan. So description of the structures, again, this is the completed project, and you'll see this photo a couple times throughout. Oh, let me go back. First and foremost, we have a 3-story office complex, a fairly straightforward stone column project here, but I'll get into a little bit of the details of that building. Next, we have the 1,250 space parking structure. As you can see here, the apartment building stretches around 3 sides of that parking structure. And so the parking structure was built inside of a permanent shoring system that we built, and the apartment building and the office building to the left were constructed at a higher grade. Now, lastly, we did a movie theater as well, and so basically all 4 sides of the parking garage have structures surrounding, and all of those structures, the office building, the apartment, the parking garage, and the theater, all required ground improvement, stone column ground improvement, or in one case, grouted columns. At the bottom of the slide, you'll also see that large MSE wall. The overhead shot doesn't do it a lot of justice in terms of its size and scale. To the top of the picture would be north, and just for orientation, the Missouri River would run north and south just to the right of your photo here. Here's a boring location plan. There were several more holes drilled on this particular site. The main reason I want to show this boring location plan, it was from pretty early on in the project development. The project changed a little bit in scale and type of structure, but this generally shows the structures on the site. Towards the top of the boring location plan is the office building, and then at the very bottom, the L-shaped structure is the movie theater with the parking garage right above it. The main reason I wanted to show this is so I can call out a soil profile through this and show not just the locations of the structures, but the grade change across the site, in addition to the soil conditions. So I don't know how well that you can see that on your screen. In the upper left-hand corner, you see a contour of 510. Towards the lower right, which would be the Missouri River, the lowest contour is about 460. So here you see about 50 feet of grade change across the site. I'll call your attention to line BB, which is the profile line that I selected for this presentation, more than anything to show the grade change across the site and how the soil conditions changed accordingly with that grade change. So here's a profile. Left to right would be the Missouri River would be off the page to the left, so you're grading up to the higher elevations. Finished floor elevation for that 3-story office building was about 502, and about 32 feet below that was the finished floor elevation for the parking garage. So as I mentioned earlier, and you can see, hopefully you can see some of the blow counts and the types of soils here. Again, this is just one soil profile. But what I want to point out here is that on top of the bluff, if you will, to the right and the higher elevations, you see the cohesive material. And it's pretty good cohesive material. I mean, you can get some pretty high bearing pressures out of this, and you see blow counts in the range of 8 to 15 or so, and in some cases even a little bit higher than that. So you're talking about medium stiff to stiff clays, and you might be wondering, why would you need ground improvement in that soil? Well, the reason why on that particular building they required 8,000 pounds per square foot. So you're not going to get that out of that clay, and therein lies the need for stone column ground improvement. As you move from the high side down to the low side and more towards into the floodplain part, you'll see that the soils change to more sands and silty sands. And I know we show mostly sand in this particular profile, but the sand, I don't know off the top of my head a percentage of silt, but there were some fines in there. It was not necessarily clean sand. And even those blow counts were pretty good, but again, that parking garage structure also required 8,000 pounds per square foot. So it's because of the different soil types across this site, well, at least one reason why we had to differ our installation techniques 2 or 3 different times. Just about every way you can install a stone column, we had to do that on this particular site. So just to summarize, we have a big grade change across the site, as I mentioned, about 50 feet. The earth retention ended up being about 32 feet. That was the delta between the finished floor elevation of the office building and also the apartment building on top of the earth retention system and the finished floor elevation of the parking garage built inside the earth retention system. And I'll show that in some photos. As I mentioned, the site soil is variable across the site, pretty good materials, but generally cohesive in the upper 20 feet. So we use one technique for stone column installation in the upper soils, and then change that technique in the lower soils and the parking garage elevation. And again, all structures on this site require stone column ground improvement to achieve a structure that can be built on spread footings as opposed to deep foundations. If you're not familiar with vibro ground improvement, vibro stone columns, again, Dr. Stuedlein touched on this. Here's some photos and an illustration on the right of a typical tool used for the installation of vibro stone columns. The illustration on the right shows the guts of the tool, which is an eccentric weight that rotates around an axis that provides a really high-frequency vibratory energy. These can be powered either hydraulically or electrically. Ours are hydraulic in nature, and the middle photo shows a typical setup of that, and that can be either, we can either pre-drill a hole to advance that tool or just push it into the ground. The photo on the left looks a little bit different, looks a little bit more robust, and it's not necessarily more robust, but the difference is that it's set up for what we call a bottom feed installation. There's a steel tube trimmie that's welded to the tool, an open hole at the bottom for trimming rock to the bottom, which we would use in a collapsible type of a soil. And I'll go into that in a little bit more detail. So I know Dr. Stuedlein talked a lot about design. I want to touch on it a little bit here. Got ahead of myself again. Figure out the animations. And we're looking at some different principles here depending on the soil type. With aggregate pier ground improvement in cohesive soils, you're looking predominantly at a reinforcement mechanism, reinforcing those cohesive soils, not necessarily an extensive amount of improvement in those cohesive soils. Alternatively, in granular soils, with the high-frequency vibratory energy, we're going to densify the granular soils. As you get into kind of the in-between of those, maybe silty sands, again, a high percentage of silt in sandy soil is going to be more of a reinforcement mechanism than densification. There becomes a limit at what we can densify as your fines content increases. So the primary reason for using stone column ground improvement more often than not is to support a uniform increased bearing pressure. And I show here a typical range of bearing pressures, which we often see 5 to 6 or 4 to 6 KSF as a requirement for spread footings and using ground improvement. In this particular project, we went considerably higher than that with 8 KSF on all the structures, but we were able to do so because we were starting out with some pretty good soils. From a bearing pressure perspective, when stone columns are designed, we're going to look at the factor of safety with respect to bulging. And that relies on the strength of the adjacent soil to the stone column or surrounding the stone column. So we need some soil strength of the existing soil to push back as the stone column is loaded. So in theory, although it's a high modulus material with you having compacted stone, in theory when you load that, you're pushing out on the soil and it's pushing back. So if that soil is extremely weak, we can't make stone columns work. However, in this particular case, when you need 8,000 pounds per square foot for your spread footing load, you need to be starting with pretty high strength soils. And as I pointed out in the boring location plan and the soil profile, those blow counts and the cohesive materials were pretty stiff in nature, medium stiff to stiff. So if we're starting out with material that's pretty good, cohesive material, then we can also get some pretty high loads on stone columns. Another big factor to consider when designing stone columns is the settlement. In particular, if you have large footings or a mat foundation, large earthen embankments, things like that, where your settlement bulb is going to get taken fairly deep, because the settlement is a function of the combined settlement of your stone column treated layer in addition to the layers below that. I don't think settlement necessarily governed. We didn't have any really large footings. We were trying to get that higher bearing pressure on this particular project. This slide shows a few different setups for stone column installation. The upper left-hand photo is a mast attachment for, kind of looks like a drill rig from a distance, but we're able to crowd that tool in the ground and can put about 40,000 pounds of down pressure on that tool. It's configured for bottom feed in this particular photo. I'll get into that a little bit with some illustrations. The traditional means in the photo that Dr. Stuedlein showed with stone column ground improvement is where you're hanging a vibroflot from a crane. We would often have to do that dictated by depth. So if we're going greater than about 30 or 35 feet deep, then we would most often set up a crane to get to those depths. However, on this particular project, if you see that photo to the right, the reason we went to a crane is because of the proximity to the existing earth retention system. So I'll go into that in more detail as well. Then the lower photo is also a mast attachment for an excavator. Again, it's a vibro flot mounted to the boom. We can put about 40,000 pounds of pressure on that tool too. So we can either pre-drill a hole to install the stone columns, or just, if the soil is soft enough, just advance the tool into the ground and open up the hole by displacing the soil laterally and then dumping those lifts of stone from the ground surface. And here's an illustration of dry top feed. So we're going to advance that tool in the ground, take the tool out, or pre-drill the hole depending on the soil strength, dump in the lifts of stone from the ground surface and compact them accordingly. However, if we're in a more collapsible soil, we can bottom feed the stone. This is what we call a dry bottom feed, so there's no water flush through the end of the tool, but we're concerned with hole collapse in this particular case, so we won't take the tool out of the hole until the stone column is complete. If we are in a sand, or maybe more particular silty sand, we can use a wet top feed to help advance that tool. We often see this in deeper applications, again in silty sands, where you're using water jetting through the end of the tool, not only to help you advance the tool, but also to help keep the hole open so stone can be dumped from the ground surface and again compacted in lifts. If you recall in the factor of safety of bulging slide, when I talked about having sufficient lateral strength of the soil to resist load from the stone column, in cases where we don't have that sufficient lateral strength, in other cases, such as very weak soils, your organic soils and peats and things like that, where you do not have any strength of that soil, we do have to go to a grouted type of an element. Oftentimes referred to as a rigid inclusion, or what we would call a vibro concrete column. On the Streets of St. Charles project, we did use this technique. However, it wasn't because of the soft soil. It was more of a load transfer condition that I'll show on another slide. So just to summarize the ground improvement on this particular project, we had a 3-story office building, as I mentioned, 8,000 pounds per square foot there. All of them had 8,000 pounds per square foot. 5-story residential tower surrounding the earth retention system. The parking garage installed at a lower elevation in sands. And the movie theater, which we used both stone columns and concrete column ground improvement. This is a plan for the stone columns. Again, relatively straightforward. This is for the office building, 3-story office building. So all of the spread footings and with the continuous and isolated footings would have stone column ground improvement. And just a shot of installation on that structure. As I pointed out, the soils were pretty stiff there, so we did have to pre-drill. That's a drill rig in the background. We are pre-drilling the hole, dumping in the stone in lifts and compacting it with the vibratory probe. This particular rig is configured for bottom feed, but it wasn't required on the stone columns on this structure. I'm not going to go into a lot of detail on the earth retention system, but in terms of the sequence of construction, you see the completed office building towards the top of the photo. The three sides of earth retention here, again about 32 feet of cut there. One thing I will point out is that you see, hopefully you can see white dots along all sides, or at least 2 1/3 sides of the earth retention system, and those are completed stone columns that needed to be field located and installed to miss the tiebacks of the earth retention system. So just one of the many challenges on this particular site with an earth retention system and stone column construction on top and bottom of the earth retention system. Just a picture of some stone column installation. This is a permanent shoring system. I want to call your attention to this side of the wall, the permanent shoring wall, and point out that we had stone columns for the parking garage in the lower elevation and stone columns required for the movie theater just adjacent to and behind that wall. Some challenges presented there that I'll get into. This is a design of the foundation plan with stone columns for the parking garage, about 750 stone columns here, and some very unique challenges in those. Not just the soils, but because of the proximity to the earth retention system. If you look on the left-hand photo, you see some of the completed footings, and in the foreground, in the right-hand photo, they're in the background. So you see how close the footings for the parking garage had to be to that permanent shoring system. And to complicate matters, the soils in that lower elevation were sands and silty sands. So in concern with hole collapse, we use a water flush to help keep the holes open to advance the probe. And our bottom feed technique, which has hoppers mounted to the tool, would not have physically been able to get close enough to the wall to install the column. So we did have to do this crane-suspended vibroflot stone column installation. You see how close we were to that wall. And in the rest of the footprint of the parking garage, we were able to use a more traditional dry bottom feed installation technique. And this is a case where we have a couple of hoppers configured on the machine. We're loading the hopper here from the ground surface. Get ahead of myself again. And then here you see a different view of that bottom feed installation where that one hopper feeds the other hopper, and that goes into a trimmy to allow for lifts of stone to be placed in the hole without taking the vibro probe out of the hole. So moving on to the theater, my animations. As I mentioned, all structures, 8,000 PSF. This particular structure did require some uplift anchors. The uplift anchors we installed here consisted of single bar grouted in concrete and tied into the footings. Having a delay on my animation here in my next slide. What I think this is going to tell you is, so with the proximity of the theater to the back of the existing permanent shoring system, we had some concern with the load of the building being transferred to the back of the shoring wall. So as you see in this illustration, if we would have just used stone columns on the left side of that structure, we were concerned with as you load the stone column and it's pushing out on adjacent soil, we didn't want it to also be pushing on the back of the earth retention system. When that shoring system was designed and built, we didn't necessarily know that the theater was going to be that close to the wall. And due to our concern with that, we wanted to get the load below the bottom of the shoring system. So in that case, we used those vibro concrete columns that I pointed out in the illustration to transfer the load lower than the back of the wall. So we didn't put any undue loads on the back of the shoring system. One thing I'll point out here, our foundation plan there is just a bit of a mess, but we have the green row of columns in the upper right-hand corner. The note there, I don't know if you can read that, says field verify tieback locations for the installation of VCCs. So of particular concern, not only the load on the back of the wall, but that we missed existing tiebacks, and we did not hit those tiebacks. We did have to field locate those. Just have a couple more slides here, and I'll wrap up. This is a shot of us installing ground improvement for the theater at the bottom of the picture. So the parking garage is done, the apartment building is done on the outside of the parking garage, and we're installing stone columns here for the theater. As I mentioned, that one row, or at least two rows right next to the shoring system, we had grouted columns. So there's a hose that goes to the tool, and we're pumping concrete into those columns. And here you see another shot pretty much of the finished product, or finished project. All structures in place, a very nice mixed-use project where we're able to use several different types of ground improvement installation. I do have one question here. Were any of the stone columns designed to carry shear or uplift loads? That might have been placed before I mentioned the uplift on the theater. We did have I didn't point it out in the foundation plan, but several of those column locations did require uplift, in which case we used the grouted column. I think I have time here. I only had that one question, so go back. In the upper right-hand corner, you see a grouted column with a single bar, and you might have multiple grouted columns with single bars tied into the footing to provide that uplift resistance. So don't know if I have any other questions. Doesn't look like I do. So again, thank you for your attendance today, and thanks for the opportunity to present this project.
Thank you, Lyle, for your presentation. Our final presenter is Dr. Louis Briard. Dr. Briard is a distinguished professor and holder of the Spencer J. Buchanan Chair in the Jeffries Department of Civil Engineering at Texas A&M University, and a distinguished member of the American Society of Civil Engineers. Dr. Briard is going to present on the Washington Monument, long-term behavior of large mat foundation under high load.
Thank you, Sadiq. The Washington Monument was built in honor of George Washington, the first president of the United States. And due to the historic events and excessive settlement, the monument was constructed in 3 phases. George Washington died in 1797, and it took people about 50 years to raise the money to decide what kind of structure they would erect in his memory. Started in 1848 with the first phase of construction. In 1858, construction stopped because they had run out of money, but they were not finished with the project. Then Civil War took place. Back to the construction in 1879, and the settlement had been so large that underpinning was selected. And then the completion of the shaft took place and finished in 1884. So the settlement was measured during the second phase, starting in 1879, providing valuable long-term settlement record. So this is a map of Federal City, which was the name of Washington before it was named after George Washington. And the green lines represent the boundaries of the Potomac River in 1792. whereas the blue lines show the boundaries today, or at least 10 years ago or so. So a lot of the landscape in Washington has changed over that time. And back in 1848, when they started to construct the monument, it was actually quite close to the edge of the river, and they had to move it off a little bit because the soil was too soft. So this is on the right-hand side, you see the early photos of construction. 1848, Robert Mills is the architect in charge. The original foundation consists of stair-stepped pyramid made of blue gneiss blocks, and the foundation is critically under-designed. The shaft is very heavy, made of marble blocks, and the construction is halted, as I said, in 1858, while the structure is about 55 meters high due to lack of funds. And if you look at the monument today and you look carefully about 1/3 of the way up, you will see that there's a difference in color between the marble that was used in the first phase and the marble that was used to finish the monument all the way to the top. The construction did not resume until 1879 after the Civil War, and Lieutenant Colonel Casey of the U.S. Army Corps of Engineers took control. And Casey was a very bright fellow. He realized that although there was no settlement measurement, the early part of the structure had settled dramatically, and he could not finish the job, or we probably would have today the Leaning Monument of Washington. The original foundation was considered inadequate, and Casey decided to increase the foundation area and to found the monument on a stiffer soil. Again, the completion of the monument goes to 1884. So this is a cross-section of the monument. You can see on the right-hand side the beige area is the initial blocks of blue gneiss that formed the early foundation, and then the green and pink areas represent the underpinned foundation, much larger, about 38 meters, 120 feet square foundation. It's kind of a square donut, if you wish. The load, on the vertical axis you have the load, and the horizontal axis you have the time. So we start in 1848. The load gets to be 300 meganewton, and 100 meganewton is about 10,000 tons. So if you want to go from meganewton to tons, you multiply by 100. So 30,000 tons in 1858 when they stopped, and then a period of time of inaction. The monument is 1/3 of the way up, and then underpinning takes place in 1878. The load increases because of the increase in weight of the foundation itself. You can see that the foundation weight increase is about 15,000 tons. So that alone created some settlement, and Casey must have been a bit worried when he saw that his repair technique was actually creating additional settlement. Nevertheless, he was able to complete the monument, and at the end it was about 600 meganewton, or about 60,000 tons. However, the important point is that if we now look at the pressure, so on the vertical axis, instead of load, now you have pressure as a function of time. The pressure reached over 500 kilopascal, or about 5 tons per square foot, at the end of the first phase of construction, but due to the underpinning and enlargement of the foundation, while the weight of the structure increased significantly, the pressure decreased according to the area. And so that by the end of, and the completion of the monument, the pressure was around 460 kPa. KC realized that he could not afford more pressure under the monument and that enlargement of the foundation needed to reduce the pressure even though the weight would actually increase. So if we now look at the weight of the original foundation, about 7,000 tons, the weight at the end of phase 1, 30,000 tons, the weight of the new foundation, 15,000 tons, the weight of the Washington Monument completed, 600 meganewton or 60,000 tons. By comparison, the San Jacinto Monument in Houston is about half that weight. The Tower of Pisa is about 1/4, and the Eiffel Tower less than 1/6. Around the monument, there has been a lot of borings, and you see the plan view here of the borings around the monument over time. And we use those borings to create a cross-section of the soil stratigraphy. And you can see that the blocky zone representing the early foundation was actually resting on the sand and clay layer, which, as I will show you, was quite weak. Below that, you have the green layer, which is sand and gravel and clay. And then you have the blue-purple layer, which is a stronger blue clay. And then about 20 meters deep, you have schist, so you have the bedrock at about 20 meters below the foundation level of the monument. The soil properties are actually fairly extensive, collected over time. And I need to acknowledge here Musa Rutledge for sharing the data with me about 12, 13 years ago when we got interested in studying this case history. So here you have, well, it's cut off. You have water content on the left, and you have the plasticity index on the right. Continuing with soil properties, you have on the left, you have the pre-consolidation pressure, and on the right, the compression index. More data, under-inch shear strength on the left. You can see that the under-inch shear strength of the underlying blue-purple layer is between 70 and 100 kPa or 0.7 to 1 tons per square foot. And then the blow count on the right-hand side is quite low in the upper zone. It reaches almost 100 in the sand layer where the underpinning was resting, and then low again in the lower clay layer. Here's some more data, the recompression index, coefficient of consolidation, and we use those to do our calculations. So basically, you have a large mat at some embedment depth, and there are basically two major issues: the bearing capacity of the mat and the settlement of the mat. So with the bearing capacity, you can do some calculations in the case of the initial situation, and recall that the actual pressure in blue at the top here under the old foundation was about 500 kPa, or 5 tons per square foot. If you do the calculations using the under-inch shear strength, evaluated on the basis of the blow count, because we didn't have any under-inch shear strength measurements, then you get an ultimate bearing capacity of 490 kPa. The pressure is 5/10. So obviously, during the first phase, this structure was very close to failure, and you will see that the settlement calculations concur with this particular evaluation. Now, this was the bearing capacity before the underpinning, and bearing capacity after underpinning. So now we're at at the deeper elevation on top of the green layer. And if you redo the calculations of ultimate bearing capacity, remember the actual pressure at the end of construction had decreased because KC decided to underpin and enlarge the foundation. So even though the load increased, the pressure had decreased to 465, top right of the slide. If you do the calculations of ultimate bearing capacity in this case, you have the two components due to the clay, and then I included the friction on the side of the underpinning zone, and you get to bottom right, 987 kPa. So now the bearing capacity is no longer an issue, and KC can continue to finish the Washington Monument. The second part of the design will be the settlement analysis. And of course, none of this is known in 1850 when, geotechnical engineering is barely starting with some of the early work in France, for example, and in England. But Terzaghi is not even born. So back to the calculations of settlement, there are really two definitions for the depth of influence. One is based on the stress increase, and the other one is based on the settlement increase at depth. So depth at which the pressure has decreased to 10% of the applied surface pressure, that's typically what we use. That's what you find in most textbooks. But you can also define it as a depth at which the settlement is 10% of the settlement at the surface or less. And there is a big difference between those two definitions. It turns out that the zone of influence for your settlement calculation depends on which definition is used and also on the modulus profile. Here is an example of, so I'm looking here at a spread footing at the top of the slide. That is a strip footing, so infinitely long. And typically in this case, we will take a zone of influence equal to 4 times the width of the footing. If you take the definition based on the settlement being 10%, the zone, the depth at which the settlement has decreased to 10% of the top settlement, and you get to the second yellow area here, the triangular area, where it shows that the modulus is increasing linearly with depth, then it turns out that the depth of influence is 1B, not 4B. It would be 4B according to the stress increase, but it's only 1B according to the settlement increase definition. So it makes a difference. But nevertheless, in this case, there's not a big problem with the zone of influence because the footing, the mat is about 38, say 40 meters wide, and the bedrock is only 20 meters deep. So we're limited by the presence of the bedrock. Once you have the depth of influence, you need to find the increase in stress at depth. And we ran the finite element method with Abacus. And we got the increase of stress with depth on the left-hand side under the phase 1 foundation. And then we reran that finite element simulation for the case of the underpinning, and you see the pink profile on the right-hand side. So now we had the zone of influence, we had the stress increase with depth, and we relied mostly on the consolidation test that had been collected over time. And on the left-hand side, you see a void ratio, the classical presentation of void ratio versus log pressure, the log sigma prime versus E plot, and that I take advantage of the situation to share a pet peeve of mine with the way we plot these consolidation curves. A consolidation curve is a stress-strain curve, and stress-strain curves are typically, when you present a triaxial test stress-strain curve, you put the stress on the vertical axis and the strain on the horizontal axis, as I have done on the right-hand side. And if you do that, you see that the stress-strain curve from the consolidation test is curving upward, which is a surprise because that's unusual. for a stress-strain curve to show upward curvature in soils. And the reason it does is because the influence of the steel ring is becoming more and more prominent as you increase the stress. And this has to be recognized, and you can see that directly when you plot the consolidation curve as stress versus strain. This is another example. I'll pass on this. So we used the consolidation curves that we had and did some calculations of settlement under phase 1, phase 2, and phase 3. And you see the cases here under phase 1, that's the old foundation with the limited amount of area and a fairly large weight, and we get 1.328. These A, B, C are different cases of level of the water table, but overall about 1.4 meter. So 1.4 meter is approaching 5 feet of settlement. So that structure really went down during that first phase. And then after the underpinning, the additional settlement using the consolidation curve limited to about 4 or 5 inches or so, 0.116, and the measured settlement 0.119. I mean, I must admit that I was surprised by how close the predictions were to the measurements. This is rather unusual in geotechnical engineering, but that was the case in this particular case. So here is the reconstructed settlement of the Washington Monument, settlement of the vertical axis in meters, and then over time a record that spans from 1848 to 1994. And you see the gigantic settlement at the beginning, the period of inactivity, and then the settlement after that. The settlement was actually monitored. KC decided to the benchmark was actually the Meridian Stone, which is in front of the White House in Washington, and he decided to put some reference points at each corner of the top of the original foundation and monitored the settlement starting in 1879. So he got some readings, and here is the settlement. Note that there was about 2 inches settlement during underpinning, and as I said earlier, that must have made KC a bit nervous when he was trying to fix the problem. Then he finished the construction, and there was an additional 3 inches or so. Note that the monument has been going down steadily, 1 millimeter per year for 110 years. So that's a good example of creep settlement. The pink line on this slide and the green line on this side are what the consolidation theory would give us. So there is definitely a need for very long-term settlement to add the creep settlement in this case. So in conclusion of this first part, after phase 1, the pressure was close to the ultimate pressure, and the settlement was about 1.4 meter. So it was close to being a very, very big problem. Fortunately, it went down very straight, and every time I go to Washington, I look at the monument to see if it's leaning one way or another, and I cannot detect any leaning. So fortunately, it went down straight. The underpinning saved the monument by reducing the net pressure on the soil and increasing the ultimate bearing capacity. Calculated settlement, phase 2, phase 3 match well the measured settlement, a bit of a surprise to some extent. Creep settlement, 1 millimeter per year for 120 years. And the role played by subsidence in the Washington Monument continued to be studied. For those settlement calculations, we actually read the consolidation curve directly. We did not reconstruct, through the Casa Grande construction and things like this. We did not use the reloading part. We simply used the early, the version curve, if you wish, considering that basically when the sample comes to the laboratory and you extrude it, the first thing that happens is a recompression of the sample. So the first part of the virgin part of the consolidation test is actually a recompression of the sample. So that's my suggestion, that you plot the consolidation curves as a stress strain curve, just to get a sense of the influence, where the influence of the steel ring starts to be excessive. And then beware of the unload-reload loop. I personally don't like unload-reload loops. They can tell you whatever you want. If you want a high modulus, you don't unload much. If you want a low modulus, you unload a lot. And so the extent of the unload really changes the value significantly. I'm going to take another few minutes to tell you in a few slides, maybe 5 slides, a parallel monument built in 1936 in Houston, the San Jacinto Monument, to celebrate the 100-year anniversary of the victory of Sam Houston over Santa Ana at the river, the San Jacinto River. The monument was built in 1936. Ray Dawson, a professor at the University of Texas, was in charge of the foundation design, and he was a very smart fellow and decided to monitor the settlement. So we have settlement of this structure ever since 1936, all the way to, in this case, 2006 was the latest measurement. We've published several papers on this monument, and one of the interesting factors is at the monument we were able to get the end-drain shear strength, and because the settlement was measured, we could back calculate the magic modulus, elastic modulus, that would give us the right answer. And it turned out that in this case, the modulus, and you see it in red on the slide here, is of the order of 120 times the end-drain shear strength. Note that the settlement of the San Jacinto Monument is about a foot. So, you know, today these structures are not designed for that much settlement. A note here on the modulus subgrade reaction. I would urge you not to use the modulus subgrade reaction. It's a flawed parameter, basically because it depends not only on the soil, but on the size of the foundation. And I show it here. K is P over S. If you use the elasticity equation, then you get to a K value that is a coefficient I times the modulus divided by the width of the foundation. So K depends on the soil parameter and on the size of the foundation. So if K is 20,000 kilonewton per cubic meter for a 1 meter footing, let's say you do a plate test to back calculate your modulus subgrade reaction, then K should only be 2,000 for a 10 meter footing. And using the same K for the 1 meter and the 10 meter footing leads to some serious surprises. One issue we addressed in Houston has gone down about 10 feet over the last 100 years because of pumping. This is the record of a well near the monument. You see 1936, the water level was 5 meter deep. In 1976, it was 90 meter deep. And then Houston decided to stop this because it was creating some problems. And they started to get their water from a nearby lake rather than pumping it from the underground. And the water level has gone back up significantly since that time. And this is an overview of the subsidence issue on the Google map. The issue of subsidence was raised by John Folk as we were studying the monument settlement, and he told me that I should look at the influence of subsidence on the difference in settlement between the benchmark and the monument. And my sense at first was, well, subsidence is a very large area type of phenomenon, so the settlement of the benchmark and the monument should be the same. Well, it turns out that that's not correct. and I show on the left-hand side here the effective stress versus depth. And the effective stress in 1975, because the water level was much deeper, was a lot higher than the effective stress in 1936. And that created a change in effective stress that has actually different influences on the benchmark and the monument. The reason is that the benchmark soil, the soil under the benchmark, is at an ambient stress level, a confinement stress level, much lower than the ambient stress level under the monument. And so we're on different stress strain curves under the benchmark and under the monument, as I show on the right-hand side. The increase in confinement makes the soil stiffer under the monument, but the fact that you're at a higher strain level under the monument makes the soil softer or weaker, if you wish. So there is a balance, and we studied that by finite element method, and it turns out, long story short here, that there is a difference of about 33 millimeters, the benchmark, between the benchmark and the monument. So the recorded settlement is 328, but should be corrected for this subsidence influence to about 295 millimeters. So this is my last slide, and I'll finish with a question. You don't have to answer it, but maybe you can think about it. Two tall structures settled significantly, the Washington Monument and the San Jacinto Monument. One settled 4.6 feet, the other 2 feet. Both performed very well over time. Modern tall structures typically settle a lot less. What is the allowable settlement of tall buildings? I don't think we have a good answer for this. So this concludes my presentation. I do not have any questions, and I'll turn it back to Sadiq. All yours.
Thank you, Dr. Beard, for sharing this great case study with us. And it's very much learning for us. And that's the end of our web conference. I'd like to thank our speakers for their valuable time and effort, our viewers, and the ASCE Geo-Institute for arranging such a nice and effective conference. Thanks. Special thanks to Keller, our gold sponsor. If you have any further questions, please feel free to contact directly to our speakers. Thank you very much, and goodbye.